Welcome to our very first online lecture. You should have your density PowerPoint sitting in front of you. You will also find it helpful to have your pencil and your calculator. Today with density, we're going to be taking everything that we've learned so far and we're going to put it all together. So we'll see sig figs again. We may see dimensional analysis coming up again. We're going to see a practical application of all of those things that we've done so far. So let's begin. First off, let's start with what really is density? What is the definition? And we've talked about this before. We know that density is a measure of mass per unit volume. So we need to make two measurements in order to calculate density. We need to find the mass of our object and we need to find the volume of our object. So I have a question to pose to you. Which has a greater density, Diet Coke or regular Coke? How can we figure this out? We need to think about how are these two things different. Jot down some of your ideas in this space provided, and I'll bring a can of each, Diet Coke and regular Coke, to class, and we'll try and figure out which one has the greater density. A few things you'll want to know about density or some density facts. This is one of our first tools that we have for identification of a substance. It can be used to identify a substance. And we will talk about several different identifiers through the year. The first is density. We know that each substance has its own unique density. If you have a way to determine a substance density, then there's a known list of densities that you can compare it to, and you'd be able to identify your substance. Another little fact that we want to keep track of is density changes with temperature. And the best example to think of when we're thinking about how does density change with temperature is, why don't you get yourself a glass of ice water? And in that ice water, you have water in its liquid form and you have water in its solid form. These two things do not have the same density because what happens? The ice cubes are floating in that water. What happens when you change temperature? Do you change mass or do you change volume? What we do is it changes the volume. So density depends on temperature because volume depends on temperature. Lastly, some common units that we will have for density, and you probably already know what these are. We have to have a mass unit and we have to have a volume unit. We typically use grams, and it's going to be per milliliters, our common unit in chemistry. Or we can also have the gram again, and use the cubic unit of centimeters cubed. That would be for if we were measuring the length, the width, and the height, we would find that cubic unit important to us. So now let's look a little bit more into density. Here is the density formula. There are several different ways that you can write this. You can write it as D equals mass divided by volume, or probably the easier way is to use the D and then do M over V. Now, if you want a cute way to remember how to do density, density equals a broken heart. The top of the heart is the M, and the bottom of the heart is the V. There's another way to remember density. Okay, so let's do a little density problem. I want you to be careful here and watch for what work I show, because when we work problems in class tomorrow, I want to see these problems that you're working out. So please make sure to include all of your work. Our problem is, suppose a student finds that 23.50 milliliters of a certain liquid weighs 35.062 grams. What is the density? And I want you to be careful for the work that I show. In these problems, we're going to start by writing down our given information. In this particular case, our given, we have two numbers up here. We have 23.50 milliliters, and we have 35.062 grams. So these are two pieces of given. What is milliliters the unit for? Volume. So we know the volume, which is 23.50 milliliters. And we also know 35.062 grams. And grams is the unit for mass. So we have our two pieces of given information. Now, what did the problem ask us to find? We are looking for the density. So you can write a D, put a question mark because that's what we're looking for. And once again, those units are really, really helpful. Please make sure you keep putting them on. If you show all of this work right here, given and find, you will earn 1 point on every single problem. The next thing I want to see you do is write down our formula. D equals M over V. If you write that down, you will get 1 point for your problem. Next, we want to plug in our numbers. So we'll still have density equals. And for our mass, we'll put 35.062 grams with the unit. And in for our volume, we'll put 23.50 milliliters in for our volume. Make sure, notice I put both my units on. If you can plug in the numbers, that's worth 1 point. Now we're down to our final part where we're going to do our calculation. This is a division step, so we'll take 35.062, divide it by 23.50, and what do we get for our density? Now be careful here because you got to remember to use your significant figures. How many significant figures does 35.062 have? It has 5 sig figs. And 23.50, it has 4 sig figs. So for our answer, we're only going to be able to have 4 significant figures, which gives us 1.492 grams per milliliter. Now this is worth the most out of your entire problem. You get 1 point for the answer. You get 1 point for the sig figs being correct. And you get 1 point for having a unit on your answer. So this final part right here, this is worth 3 points total. So this is a 6-point problem, but guess what? You can do something wrong on your calculator, but as long as you have everything else right, you're still getting 5 out of 6 points. It's always about the partial credit. So this is our basic density problem that we're going to work. Now I'm going to show you what are some other things we can do with density. We can use it not only to solve for the D, but we can also solve for the M and for the V as well. We will look at that in a little bit. First, let's tackle a little bit with volume. The volume can be measured in 2 ways, and we've talked about one of these a little bit before. We can do it by the measurement of length, width, and height, and then using this volume formula, which I would highlight, you can solve for the volume taking length times width times height. This is where we get that cubic unit that we looked at before. So why don't you take a second or two, pause the program, get a ruler, and make the following measurements in centimeters for your chemistry textbook. You want to measure the length, the width, and the height, and then using your volume time equals length times width times height, solve for the volume. Write it down here on this slide, bring it to class tomorrow so that I can see. This is one way. This is for when you have an object of known shape, like a cylinder. This would work for a sphere, a cube. We have lots of different volume formulas. You just have to get the right one. Now, what do we do with the units on that last problem? Because you got to be careful. Did you get that cubic unit? Cubic units, just like the other units that we looked at, they can convert to other cubic units. Using the dimensional analysis just like we've done before, except it's going to take a little bit more to get there. We're going to have to do a few more conversions. So here, if we have 5.68 times 10 to the third cubic centimeters, well, where do we need to go first with this? Well, with the way that we're doing it right now, we're going to have to do a couple of conversions. Right now, we've always been converting to the base unit, so we need to do that first. Centimeters on the bottom to cancel, meters on top. Notice I didn't put a cube on either one of these. That's because I have to convert for both the length, and then I have to convert for the width, and then I have to convert for the height. I have 3 conversions that I have to do there. So, but in each place, it's going to be the same information. 1 meter equals 1 times 10 to the second centimeters. Now, let's go ahead and get rid of this multiplication here. We're not going to need that quite yet. Okay, so this centimeter here cancels out the cube, leaves us with a square. This centimeter cancels out the square and leaves us with a centimeter. That centimeter cancels out that centimeter. Now we're to an answer that's going to be in meters cubed. So we'll take 3. Since this is a division step, we're going to subtract 2 and get 1. We're going to subtract 2 again, and we're going to get negative 1. And then we're going to subtract that final 2, and we're going to get negative 3. So we end up with 5.68 times 10 to the negative third. And in fact, I think that's all we're going to do here. Cross out decimeters cubed. We're just going to make that a meters cubed. We're going to go straight to the base unit. So you may see some cubic units on your homework. Don't panic if you see them, especially if it's centimeters cubed. You can probably just use it. But if necessary, watch out. Sometimes we have to do these conversions, and it requires 3 conversions for the length, the width, and the height. Okay, where are we next? Another way to do measurement of volume is what happens when you have these weirdly shaped objects. Like, for example, Mrs. Gill really isn't a normally shaped object. There's cylinders, there's spheres, there's columns, all of these different shapes. Well, you can't take measurements with a ruler and come up with the volume. What we're going to do is the water displacement method. And for these irregularly shaped objects, we're going to submerge them in the water and see how much volume or how much water they displace. And I'll show you how to do this in next class. We're not going to submerge Mrs. Gill, though. We're going to use something else. Okay, so finally here, we have a series of 3 types of problems that show different uses of the density formula. For solving for volume, watch carefully again for the work that you need to show. Mercury has a density of 13.6 grams per milliliter. What volume of the mercury must be taken to obtain 225 grams of the metal? Start with your given and find, and we'll start there in just 1 second. Did you figure out what your givens are? We have 13.6 grams per milliliter, and we have 225 grams. So for our given, we'll write, this is in grams per milliliter, so that is our density. Remember last time that's what we were solving for. And we have our mass, which is 225 grams. This time our find is going to be what volume of mercury would we need? So we're looking for volume, question mark, that's going to be in milliliters. And remember, once again, you show this work, you get 1 point. Now, we always start with the basic density formula. So we're going to start D equals M over V every single time. Here's the problem, though. You can't solve for something that's in the denominator. So first, we've got to get it out of the denominator. The easy way to do that, multiply both sides by volume. That cancels volume over here, and now gives us volume times density equals mass. Wait a second. That's not the formula that we're looking for, but it could be a useful formula because it does allow us to solve for mass. We've got mass this time, so we're going to go one more step. This time we're going to get rid of density, and we're going to divide both sides by density. Cancels here, and that gives us volume equals mass divided by density. We have rearranged our equation. Now we are ready to plug in. Okay, so you showed me the original formula, you get a point. You showed me how to move it around, you get a point. And lastly now, we're going to start plugging in our numbers. Our mass is 225 grams, and our density is 13.6 grams per milliliter. Look at those sig figs again. 225's got 3 sig figs. 13.6 got 3 sig figs. So our answer will be able to have 3 sig figs. Take 225 and divide it by our 13.6. And we get 16.5 milliliters. Once again, our gram cancels our gram. So, final points here. Whoops. You get 1 point for your plug-in, and then once again, this final answer is worth 3 points because you showed me you know how to use your significant figures, you showed me you know to put a unit on, and of course, you've got the right answer. Remember, as we're going through, if anytime you need to pause, go ahead and pause, jot everything down, and then pick back up again with the lecture. Okay, let's try another problem. This time we're solving for mass, so we're going to use that formula we came up with before. Once again, watch carefully for your work. What is the mass of 19.9 cubic centimeters of coal? Okay, so I've got a number and a unit there that has a density of 1.50 grams per cubic centimeter. Another number and a unit there. Once again, we always start with our given. For our given, now this is a cubic unit that we have there, so that's volume equals 19.9 cubic centimeters. And we know that our density is 1.50 grams per cubic centimeter. This time they asked us to solve for what is the mass. So our find will be the mass, and we're looking for that in grams. Once again, always start with D equals M over V. This is the universally recognized formula. Once again, now we want to get rid of volume because we're solving for mass. We get rid of volume the same way we did before, multiply both sides by volume. And this time, pretty quickly, we are to the desired formula. Volume times density equals mass. Plug in our numbers. 19.9 cubic centimeters, 1.50 grams per cubic centimeter for our density, and that'll give us the mass. This time we are multiplying, but remember a sig fig rule is the same as before with our division step. 3 sig figs here. Ooh, now we got a trailing 0 right there, but we've also got a decimal point, so this has 3 sig figs as well. So our answer this time can have 3 sig figs. We will take our 19.9 and we're going to multiply that by our 1.50 and we get 29.9 grams equals our mass. Now, for those of you keeping track of those point totals, 1 point here for our given and find, 1 point for the original, 1 point for turning it around, 1 point for plugging it in, and then 3 down here once again for the answer, the sig figs, and the unit. So those are 3 types of density problems that we can work. Plain old density where it's D equals M over V, solving for volume, and solving for mass. One final type of problem that kind of has a little bit of a twist is what happens when we're using the water displacement method in a density problem. How do we work with that? So in this problem, we have the mass of an object is 55.64 grams. So there we go. We've got a number and a unit. The graduated cylinder contains 75.2 milliliters of water before the metal is submerged and 77.8 milliliters of water after the metal is submerged. So we know where the water started, we dropped the metal in carefully, and the water level rose up. By those 2 numbers, we're going to be able to find out what the volume of the metal actually is. Then we'll be able to find the density. Okay, so let's start with our given once again. We have our mass, which is 55.64 grams. And this time we have 2 volumes. Neither one of these is the volume of the metal. This is the volume of the water initially before we put the metal in, so VI, which is 75.2 milliliters. And we know the water level after the metal was submerged, the V final, which is 77.8 milliliters. What we don't know yet is what is the volume of the metal and then the density of the metal. So we actually have 2 things to find this time. We need to find the volume of the metal, and that'll be in milliliters. And then we want to find the density of the metal, which will be in grams per milliliter. Well, finding the volume of the metal really is as simple as it looks. It's a subtraction step. We're going to take the final volume minus the initial volume, and that'll give us the volume of the metal. So we have 77.8 milliliters minus 75.2 milliliters. And when we subtract that, we will get the volume of our metal, which is 2.6 milliliters. Did you get your sig figs correct there? Did you line up your decimals and mark the uncertain places? Now that we have the volume of our metal, we can find the density using D equals M over V. We will plug in for our mass, which is 55.64 grams. And we'll plug in for our volume, now the volume of our metal, which is 2.6 milliliters. Don't forget to look at sig figs again. 4 sig figs here, 2 sig figs there. How many can we have in our answer? 2 sig figs. Do our division step on that, and we will end up with 21 grams per milliliter. Once again, point totals for this. 1 point over here for the given and find. 1 point for showing me how you found the volume of the metal. A point for the density equation. A point for plugging it in. And 3 points for your final answer, unit, and sig figs. Okay, so you know pretty much everything there is to know about density. With density, we're going to be doing several labs, and these particular labs that we're going to be studying lead really well into a discussion of accuracy and precision. These are often used to qualitatively describe the reliability of a measurement. Remember, we're using that word qualitative, so that means we're talking about words to describe it, not numbers. Okay, well, what is accuracy? Accuracy is how close your value is to the correct value. A really easy way to remember this is I grade your tests for accuracy. Tests are graded for accuracy. Precision deals with the reproducibility of the results. Can you get the same results over and over again? Remember when we talked about the scientific method, we said you had to do your experiment several times and you wanted to get the same results? Well, that's talking about precision. Can you reproduce the results? Now, I don't make you take your tests over and over again to prove reproducibility, to prove your precision. But if you think back about the 2 labs ago when we did the bubbles lab, remember that we did multiple trials for each solution. We blew the bubbles 3 times for each solution. That's where you're trying to see if you can reproduce the same results. Are you getting the precision? So in lab, this would be doing multiple trials with the same result, like we did in the bubble lab. Can you think of any other ways we might be able to apply this into lab or anywhere else? Take a second and list a couple of the ways here. And then we're actually going to talk about a way how we can quantitatively describe our accuracy. And this is where we use percent error. It is used to quantitatively describe the accuracy of the data or the measurements. And you need 2 pieces of information. You need the experimental value, and this is a value found through experiment or or calculation. So this is a value that you have created by doing your experiment and doing the calculation. The accepted value is exactly what it sounds like. A value known to be true. There are several places you can find accepted values. Our textbook has a lot of accepted values listed for both density and specific heat. There's also the Handbook of Chemistry and Physics. It has tons of accepted values for all kinds of different variables. Well, what we could do is we can take these two things, put them together, and be able to calculate the percent error. And here's the formula. Percent error equals, and now we're going to put an absolute value bar here because our percent error is always a positive number. We're going to take the accepted value, subtract our experimental value. Once we've subtracted, then we're going to divide by the accepted value, and then multiply it by 100 to change it into a percent. Thinking about percent error in this formula, do you want to have a high percent error or a low percent error? Jot your answer down here and we'll look at it tomorrow in class. So our last thing on here is one little problem, just so you can practice percent error. The density of an object is found to be 2.56 grams per milliliter through experimentation. The actual density of the object is 2.43 grams per milliliter. What is the percent error? So once again, what do we have given? This value, well, we found it through experimentation, so it has to be our experimental value, and you can abbreviate experimental. It's 2.56 grams per milliliter. Now we have the actual densities. That's telling us it's the accepted value. You can abbreviate that as well. That's 2.43 grams per milliliter. What we want to do is figure out what's our percentage of error here. So we're going to find the percent error. Okay, so back to our formula, the percent error equals, and if you want to abbreviate here as well, you can, the accepted minus the experimental divided by the accepted times 100. Okay, let's plug in those numbers. You can leave the units out here if you want to because it gets a little bit crowded. So we have 2.43 minus 2.56. And we're going to divide that by 2.43. Then multiply it by 100. Remember, once again, that is absolute value. So even if you come up with a negative number, you're going to make it positive. So subtract first, then divide, and then multiply by 100. And we end up with 5.3% error. Do you think that's good or do you think that's bad? Find out, think about it, and come with an answer to class tomorrow. So this concludes our first online lecture. Remember, at any time you could have paused and gone back, or if you need to go back now, you can go back and find what you need. Come to class tomorrow ready to work on some problems and start some lab work. Have a good evening.